Okay, this is part 2 of our GIS analysis short videos. And this time we're covering spatial analysis of raster data. So if we're going back to the beginning, we talked about how we represent the real world. We can represent it with vector, which is geometry, or raster, which is a field of numbers, a grid which covers our study area with numbers that can either be actual values like elevation, or it can be codes that can be linked to some other attribute table. Yeah. So analysis of raster data. So with vector data, we had our, proximity, buffer, overlay operations, and there is a different set of tools, and some are similar and some are not, that we use with raster data. And the tools that we use to manipulate raster data we can kind of lump them into a few general categories. Distance measurement operations, local operations, and we'll discuss these in detail in a moment, neighborhood operations, and zonal operations. And we'll get into some of the details on this. But first, let's talk about buffers. We talked about buffering vector data, and it's worth mentioning that raster data can be buffered as well. So, but the output is going to be raster instead of vector. So we had an example with vector data of points being buffered by a certain distance of 20 meters, 30 meters, and so on. And we can also do the same with raster data. Probably the one difference is going to be in the resolution, the cell size of the output. We can have very fine, very small cell size, which makes a very fine raster, less pixelated, or we can have bigger pixels, which use up less data, less storage, but are not as quite as, but become more pixelated. Here's a closer view of a raster buffer versus a vector one. So here we have polygons that are created at a certain distance from a point. And here we have a raster that is created at a certain distance from a point. And similarly, we can have different, at very fine scale or rough scale raster data can also be buffered. And what it does is it creates a new raster that is coded for the distance from that feature. And one thing useful too about raster is that you can, that the raster has numbers. So the numbers in the output raster would be the buffer distance. Same thing with polygons. We can create a buffer that's a vector data that creates vector output, and with raster data that creates raster output. But when it comes to distance, one other very useful thing about raster is distance measurement operations. So we can create, from a certain feature, we can create a raster where each cell, the number represents the distance from that single feature. And we have, let's say, we have a raster with two source regions, number 2 here, number 1 there. We can have it where the rasters in between have, it's calculating the true, or what's called cost weighted distance between cells. So let's pause on that for a moment. So Euclidean distance is simple, that each one is the distance in direct straight line distance in meters or feet or whatever the map units are. There is a concept also called cost distance, where you use some type of a raster that tells you how difficult it is to travel. It creates a cost of travel through certain parts of the raster layer to create barriers or things that are slow to move through. So if you think about it, let's say here, just one way to kind of conceptualize this, how far is Fresno from Las Vegas? Well, if you flew there in an airplane, that's one distance. That would be the Euclidean distance. But however, because there's when you're traveling by car, you don't have that option. There's a cost of traveling over the Sierra Nevada. So when you're factoring that in, you have a distance that is the kind of the best, most efficient way of traveling by car, considering the cost of traveling through the mountains. Cost doesn't necessarily mean money. It can just mean difficulty. A lot of these tools were developed as, the concept was cost. Like if we're building power lines, what is the cheapest way to get from point A to point B rather than the most direct way? Because you have to account for land use, mountains, barriers, and so on. But when we say cost now, it can be inconvenience. We can be dangerous habitat for a species. It can mean a number of different things that aren't necessarily about money. So here's an example, and this is from an actual project from some years back, where there was different land retirement strategies being considered on the west side of the San Joaquin Valley. And what we're looking at is the cost distance of some type of endangered species trying to travel through these different types of features. And depending on the different scenario of land retirement and, evaporation treatment areas, which would be for selenium and so on, we could compare how easily it would be for animals to move through a landscape under different scenarios. Okay, so those are the kind of the gist of the cost tools. A lot of by the way, I should so if you're into like I've worked with endangered species, the way you would use cost distance is in trying to figure out corridors for movement of species. What is the most efficient corridor for connecting different populations? So I know in wildlife, these are some very useful tools, especially the cost distance operations. Okay, other things include local operations. These are where you're actually just doing some math essentially on the raster. So each cell has a number. Remember, each cell is represented by a number. And you can do math on the entire set of numbers of a raster at one time. So, for example, you can convert integer numbers to floating point numbers, from whole numbers to decimal numbers. We can reclassify numbers so that, turn it from, so all the ones are now threes and all the threes are now fours and so on. We can do logical operations. Let's kind of walk through this in a little more detail. Simple math. So let's say we had a set of elevations that we wanted to be whole integer numbers. We can convert from one to the other. We can reclassify. If let's say we can have a condition where we can have if the number was below 50 feet, the number turns into a 1, and if it's above 50 to 100 feet, it turns into a number 2. This would be what's called a conditional operation. Like if it's true, this, if it's false, that. Some simple math operations. So let's say we had, 3 years of water level, of sea level, and we can calculate the minimum for each one, the maximum for the combination of them. Let's say these are year 3 is 24s, year 2 is 22s, and year 1 is 20s. The minimums, and we had what's called no data. And I should pause for a moment about that. that with raster, you either have number values, or you can also have what's essentially a no data, a null value. And oftentimes when you do operations on raster, these things become just like dead zones. They're not included in the calculation. They are just like, ignore this values that are to the cells. So here we have a null, a null or no data value for one of them. So it's not included in the operations. So the minimum are the 20s, the maximum are the 24s. The mean average is 22, the average between these, you can add them together, divide by 3, get the mean. You can also calculate the standard deviation. You can also do simple math operations. So if you have 3 sets of numbers, you can add them all together to get a, each of these numbers is these 3 added together. You can do the sum, or you can do, well, what is the, of these 3 different rasters, what is the majority? Most of these are 1s, most of these are 4s, and so on. You can do the number of unique values, the diversity. So this one here, we had a 4 and a 4 and a 2. We had 4s and 2s, so that's 2 separate types of numbers. Here we had a 4, a 3, and a 2. We had 3 different unique numbers between them. And we can get more complicated. Like, this is something called the universal soil loss equation, where you have a raster for rainfall runoff, one for soil erodibility, terrain, slope steepness, crop management, and so on. And these would be numerical things. And then you have this formula where you're doing R times K times L times S times, you can do a complex chain of math operations using different raster data sets and come out with some combination. And these are similar to, like, when we had the lab on remote sensing, we did different indices that were created for us for burn index, vegetation indices. This is essentially how that works. Different bands of information are combined in a way using math to create some type of new output that's more meaningful than the inputs. So here we have, this is just kind of showing raster data of land use and land cover. We have raster with aerial imagery. We have terrain, and then we have information can be combined. And so now each of these colors represent some different kind of land cover class. And this is kind of showing you what the classes look like in real life. And now here we have we can change the information somewhat so that we have the existing land cover in 2006, and then maybe predicted land cover with changes in sea level rise. So we can use raster information to do these kinds of complex types of analyses. Perhaps what's changed is the projected terrain model, the elevation model, and sea level has changed over time. Actually, it wouldn't be the terrain model, it'd be the sea level that changes over time. But we know what areas might be inundated because of the terrain model. So getting a little tongue-tied here, sorry. All right, going back to the basics. We can do things, there's some things like local reduction or magnification. So let's say we have a input raster where we just want to take maybe every other cell, but in both directions, and then use that we kind of collapse that into a smaller raster data set. Or here we want to take this raster and we want to kind of expand it so that we have more cells that retain values from some of the original cells. I don't actually see this used too much, but it's just This would be kind of more for like dealing with aerial photography where you might want to shrink it. You know, if you work with Photoshop or something, you can reduce or expand the size of your image that you're working with. And that can be done with raster tools as well. Neighborhood operations. Now these are cool. So with local operations, you're dealing with only what's in that cell. Here, you can use information based on its neighbors. So these are called neighborhood, oftentimes also called focal operations or moving window. So here we have a 5 here. And what we want to do is, let's see, I think this would be like the average. Yeah, you can do the average, the mean, minimum, you know. So here we have a 5, and we have all of these neighbors. And if we, the majority here, okay, so this is an example. So what is the majority here? What are most of the cells surrounding this 5? Most of them are a 3, so our output is now a 3 because it got that information from its neighbors. Then we move to the next one, and the majority of these are 4s, so it becomes a 4. So it's like the window just keeps moving and then just it's recalculating per cell for the output. And when you're doing this, you can define different types of windows. You can have a square window, rectangle, or rectangle of different sizes, octagons, nearest cross, so that you're using only the 4 connecting cells. And you can use a circle, which kind of uses information from the anything that's within the circle. And so there's different types of shapes you can use as your moving window. It doesn't have to necessarily be square. What you need to know, what you really need to know is how big is it, how many cells, either by in cells or in map units, then it can do the math for you, and the shape of your moving window. So here you can do, you can have the majority, minority, or diversity. So here we have land cover codes. We have, so here's what we would call qualitative operations, such as the what is the majority, what is the minority, or what is the diversity. And so here we are using a 3x3 window. So for this cell here, the majority of the cells in this 3x3 windows are 3s. But if we move it to the next set, the majority in here are going to be 4s. If we move it down 1, the majorities are 2. And then this is the minority. What are the least? This is like the least, most common. These are what are the least common. That'd be minority. Then we could also have the number of unique values, which would be the diversity. How many different, numbers occurred in this window? It was 4 different, it was 1s and 2s and 3s and 4s. That's 4 different numbers were within that window. So, in this example, this might be land cover. So we may be doing something called like land cover matrix. What is the most common land cover in an area? What is the least common? How diverse is the land cover within an area? And we could also do quantitative or mathematical operations, like getting the minimum number, maximum, the mean or average, and the standard deviation. So in this example, so here, we don't, these wouldn't be meaningful because here the numbers represent categorical data, land cover. The 3 just means forest, or the 4 means water. It doesn't make sense to do math operations on those because it's not representing any real quantity. It's just used as a code. Here, the numbers are meaningful. They actually are real quantities of elevation. And since they represent real quantities of something, you can do math on them. So for this set of squares, what is the minimum value? Well, the minimum of this is 18. So the center is coded as an 18. We move it over 1 there. This one's the minimum is 16. We could also do the maximum. We could also get the average. So within this area, the average turns out to be 19.1. And also the standard deviation as well. Zonal operations. So calculations are applied to a zone. So then the zones that can be raster, or the zones can be polygon areas. So let's take a moment kind of to consider this. So let's just we have rasters that represent, or it could be a vector file that then gets rasterized, zones. So each number, here we have 4 different zones. Zone 1, and so each cell is coded as the zone number. Zone 4, zone 3, and zone 5. And then we have our input, which is our elevation. So let's say these are 4 different study areas. What we want to know is, what is the average, or what is the minimum, or what is the average elevation within the 1 zone? What is it within the 4 zone? What is it within the 5 zone, and so on? And that's what a zonal operation is. So, okay, we have elevation values. We have zone values, zone 1, zone 4, zone 5, and zone 3. And what is the minimum? So within the zones 1, the minimum is 6s. So the whole thing is coded with the minimum value, or the maximum, or the majority, or the minority, or minority, mean, standard deviation. And so the whole zone is encoded with information that's calculated from the input raster. So this is like doing a summary by certain geography or certain areas. You're tabulating the average by zone. So here's an example. Let's say we had a terrain model, elevation, and then we have these different zones that are, that are here. And for each of these big squares, we can kind of compute the average, or the minimum, or the maximum, and so on. That's the end of this video. Thanks for watching.